So we have finally come to this last result of the section. Here we have to use the previous result, okay, the previous proposition to prove that this infinite series, let's see what the infinite series has. Its general term is this, the reciprocal of the pth power of n, where n is a positive integer and p is some real number. P is not changing. N is changing, but p is fixed. It's some real number. P can actually be negative, positive, it can even be zero, it can be rational, irrational, anything. And the claim is that this converges absolutely if p is greater than 1 and diverges if p is less than or equal to 1. And in this second condition, even those cases are also included where p can be negative. Okay. But does this not look familiar to you? Have we not already come across this result in fact? Yes, sort of. Actually, we have already proved this result, but in a restricted setting. We have proved this exact same thing in the 7th chapter, where we studied convergence of series. However, there this exponent p was a rational number. That was the restriction. Now we are making it more general and making a similar, exactly similar claim, but for any real number p. So it's not like we are again proving something which we have already proved. We have only proved a part of this general statement. Now we have to prove it in this at this generality. Okay, so let's see the proof. This proof actually is an exercise, so there is nothing, I mean no hint or anything. We just, if you go to the end of this section and see the exercise, it's simply mentioned that we have to use the previous proposition to prove this. That's it. Okay. So we are going to settle the obvious things first. Let us first see what will happen if p is equal to 0. If p is equal to 0, then you know what this series will be. Each term will now be equal to 1. And this series is divergent. We already know that this series is divergent because it's just 1 plus 1 plus 1 and so on. But if you really want to again think of why it is divergent, well, just think of what its sequence of partial sums is. It's just the sequence of positive integers. That sequence is not convergent, you can say, because it's not bounded. It's not bounded from above, so it's not bounded. And any convergent sequence is necessarily bounded. So that sequence is not convergent, so by definition this series is divergent. And that comes under this condition, p equal to 0. So okay, so the claim is matching here. If p is 0, then the series really is divergent. Alright, but that is just one value of p. If p is negative, then n to the power minus p, then minus p is positive, so n to the power minus p keeping in mind that n is a positive integer, is greater than or equal to 1 for all integers n greater than or equal to 1. Because n is greater than or equal to 1, it's like, for example, if p is minus 2, say, just simply saying, then this statement is n squared is greater than or equal to 1. That's true. Because n is greater than or equal to 1, p actually being negative need not be an integer. It can even be minus root 2. Okay, but then also you can see from the rules of inequality that this inequality you are going to have. So, by the zero test, the series is divergent. Why? What does the zero test say? The zero test is a necessary condition for the convergence of a series. If a series of real numbers converges, then the sequence of its terms should converge to 0. However, this sequence cannot converge to 0 because all of its terms are greater than or equal to 1. It cannot go past 1. Go past 1 means if you think of the real line, 0 sits here and 1 sits there. So all the terms are on that side of 1. They are not coming towards 0. 1 prevents them from doing so. So obviously they cannot converge to 0. And that is why, since the terms of the series as a sequence do not converge to 0, so the necessary condition for convergence is violated, so the series cannot be convergent, it is divergent in this case also. That is why for the non-positive values of p, that is, if p is either negative or 0, then the series is diverging. So that side of the real line has been settled for the p values. Now, so that means we can let p be positive now, because the non-positive cases have been settled and all our conclusions are matching with the claim. So we can now assume p to be positive. Here also, let us first consider this case. P is greater than 1. In this case, we have to use that proposition to prove that this series converges absolutely. But in order to use the proposition, we have to first of all define some function f from 0 to infinity to r, okay, which is non-negative and monotonically decreasing. That thing we need. So let's make this definition. Define f from, or why am I writing like this? I can write normally. By this rule. So I am carefully defining f of x to be equal to 1 if x is non-negative. Non-negative, of course, because this is the domain. Input cannot be negative. And less than 1, and x to the power minus p if x is greater than or equal to 1. Say this is my definition of the function f. First of all, I have to make sure that this makes sense. are we going to encounter any problem like division by 0? That possibility is absent here, but what about this? Well, we won't encounter any problem here because it is in this part of the domain where x is greater than or equal to 1, x is not 0. Here, where x can be 0, there is no problem because the output is 1. So, the function is well defined, nothing wrong with the function. And also, this function is going to be non-negative and monotonically decreasing. Note that f is actually positive itself, even we are not going to have 0 as output. Why do we say so? That's because 1 of course is positive, and any such power of a positive real number is also, from the theory of exponents, always positive. So that's why the outputs are positive. And where are we getting this monotonically decreasing thing from? Well, if you think of the graph of this function, just roughly I am saying, let's just think of it. The graph of course is going to depend on what p really is, but still we can get a general idea of how the graph looks. Zero is a point in the domain. Okay. Say this is your 1. Between 0 and 1, the output is 1. Here also say this is 1. Then, in this part we know what the graph is going to be. And also, this line segment is not going to touch the vertical line passing through 1. But after that, the graph will dip. Why? Well, that's because do not forget that p is greater than 0. Do you see that? And x is greater than or equal to 1. So, if x is greater than or equal to 1 and p is greater than 0, then x to the power p is also greater than or equal to 1. So, x to the power minus p is less than or equal to, because in order to get x to the power minus p, you have to take reciprocal, and when you do that, keeping in mind that both sides are positive real numbers, the inequality will get reversed. And that's how, whatever value this x to the power minus p is going to be, it will be less than or equal to 1. And one more thing, this is a decreasing function. Why? That's because as x increases, x to the power p also increases, but then its reciprocal, which is this x to the power minus p, decreases. So it's going to decrease like this without ever touching the x-axis, because the value is never going to be 0. Now, whatever we are showing here somewhat vaguely can actually be put more rigorously. If you go back to the properties of exponents, from the results there that we already have come across, you can rigorously prove that this is monotonically decreasing. I am not going to do that. Okay. At this stage, some such things we can simply mention, which follow almost immediately from previous results How they follow that we are not going to show to that level of detail. Okay, so instead we understand it like this. If someone asks you to really do it, then you should be able to do it. Okay, and I believe that you can do it. You just go back to that section where we proved those properties of real exponents. I forgot in which chapter it was. I think it was real exponentiation 2, something like that. So using them, you can show rigorously that this is monotonically decreasing. And it's also from there that we can see that this is never negative, not even 0. Alright, so our function is set. Now what? Now we have to, of course, find the supremum of some integrals, because we want to use that proposition. So this is what we are going to do. For any n greater than 1, we have this n is a real number. It may not be an integer, okay. In the context of that previous proposition also, n was just a positive real number. I will come to it and I will explain why I am not simply taking n greater than 0 and why that is enough. Let me first do the calculation. Let's see what we get. So, the thing we are now going to calculate is this. Alright. Because I have chosen n to be greater than 1, using one of the properties of Riemann integrals, I can split the integral into two integrals like this. Actually, if you go to the basic properties of Riemann integrals, that first theorem, there you see the last part where we partition an interval I into two intervals j and k, and that is why you can see I have been careful in including this point 1 in one of the intervals and not including it in the other interval, so that these two things really form a partition of this. Oh, and one more thing. How do we know that this integral actually even exists? Well, that is coming from the fact that f is monotonically decreasing. So you just see where n will lie. N lies here somewhere. Okay, say here we have n. Because f in general is monotonically decreasing on this domain, obviously if you are going to restrict yourself between 0 and n, there also it's monotonically decreasing. It does not lose that property. And we already know, we have in fact proved this thing itself in this section, that such a function is Riemann integrable on that interval in which it is monotonically decreasing. Okay, so that's why this integral actually exists and we can consider it. And then by that property we can write like this. Alright. Now between 0 and 1, what is the value? 1. That means in this interval, on this interval the function is constantly 1. So the integral will have value that constant times the length of the interval. What is the length? Length is also 1. So that means this first integral is 1. Alright, now what will be the second integral? For the second integral, the variable is greater than or equal to 1, and that's why this part of the definition of f has to be used. Okay. Now, how will you calculate this integral? Obviously, this may sound like a silly question to us because we have already done this kind of things in calculus, right? But still, for us in this book, it may not exactly be a simple question. Why? Well, let's just forget about those things and calculate this integral school style. So if I am saying school style, then I will just write the antiderivative of x to the power minus p here. Or to put it even more simply, what do you write in place of this integral? You just remember your school formula. You add 1 to the exponent, 1 minus p, and divide by that. And then you have to put the limits also. This is school notation I am using. Okay. Some people will not even use this square bracket on this side and write simply a bar here. Anyway, but now if you put, what do you have to do? The upper limit first minus the lower limit. So, n to the power 1 minus p, because 1 minus p will be there in both of the things, minus 1 to the power 1 minus p is 1. Okay. All right. Now, this thing turns out to be less than or equal to 1 minus 1 divided by 1 minus p. How? Well, for that, so how am I getting this inequality? Let's try to justify that here. So if we ignore this 1, because you can simply ignore 1 from both sides, this is what we seem to have written. 1 minus p minus 1 divided by 1 minus p is less than or equal to minus 1 divided by 1 minus p. This will be equivalent to, we have to multiply by 1 minus p on both sides. However, recall that p is greater than 1. So 1 minus p is negative. You can multiply by that, but the inequality will change direction. So if you do that, you will have n to the power 1 minus p minus 1 greater than or equal to. Do not forget that we have a minus sign here. So minus 1. And this will then be equivalent to the inequality that n to the power 1 minus p is greater than or equal to 0. Yes, it is, because our n is greater than 1, and so n after all is a positive real number. And any power of a positive real number, whether the exponent, the exponent is negative, that will not affect anything. The power n to the power 1 minus p after all is positive, because the base is positive. This means that whatever we have written here, and that's why I was writing equivalence, not simply implies. You can go back from this to this and have this. Just add 1 to both sides of this inequality, so that means this is correct. Now, on further manipulation, what are you going to get? 1 minus p minus 1 divided by 1 minus p. So minus p divided by 1 minus p, or if you adjust the minus sign with the denominator you get this. Okay. So the calculation seems fine, but we seem to have used school result. Are we justified in doing so? Well, we are. In what sense? See, in the sense of a result which we are yet to see, but which we have already used in school a lot, which is simply integrating something using antiderivative. We haven't yet got to that result that has the name the second fundamental theorem of calculus, which we will prove in a coming section. Still, we can use it prematurely here. There is no danger because this corollary that we are proving here will not be used in proving that second fundamental theorem of calculus. So it's not circular. We can use it here prematurely. But what is that second fundamental theorem exactly? Let's just see what we have used here. This is the statement of the second fundamental theorem. Suppose you have a function f naught this f on a closed interval where a is less than b, a and b are real numbers, such that f is Riemann integrable. Okay, and f has an antiderivative, capital F. What is an antiderivative? An antiderivative is a function such that if you differentiate it, you are going to get the original function. Okay, for example, the antiderivative of x to the power minus p is this. Why? Because if you differentiate this function, then you are going to get x to the power minus p. Then the second fundamental theorem says that the Riemann integral of f is equal to f of b minus f of a. This is a result. Actually, you may have wondered when we introduced integration that no, whatever we are right now doing and calling Riemann integrals, how are they related to integration we learned in school? That seemed to be something different, no? But this is the link. So what we did in school and what we were told is the definition of integration actually is a result. And that is why carefully in school we were presented with functions which not only are integrable but which also have an antiderivative, so that we can use this theorem to calculate the integral quickly and nicely, which is why we had so much problem in integration, and our integration nightmares were all about finding this capital F when small f is given. If, for example, small f is sin x, then capital F is minus cos x, we have to remember all those tables. That's what we have used here. Okay. But of course, because we are already well familiar with the process, at least mechanically, so it's okay. No further explanation is needed. But this result we will prove, okay, in a coming section. So what have we got now? We thus have integral of f less than or equal to p divided by p minus 1. All right. So, no matter what our n is, We can choose n to be any real number greater than 1. This integral value is going to be less than or equal to this real number, fixed real number. And that is why the supremum of this integral of these integrals is finite or is a real number. It's not plus infinity. Hence, or thus, by the previous proposition, what was its number? Proposition 1164. The series summation f of n, where n varies from 1 to infinity, which is just this series, is absolutely convergent. Actually, because all the terms of this series are positive, so convergence and absolute convergence are identical. Now, let me come back to that issue of this. I have chosen n to be greater than 1. Here, however, I am taking the supremum over all positive numbers n. What about the n's that are less than 1? I haven't said anything about them. So, is that a mistake? Well, actually, that's not a mistake. That's because if your n is less than 1, then the integral of f over that interval, whose right endpoint is n, will be only a part of one of these integrals. Actually, it will be this is the explanation, because it's only for our own understanding. So let me put this dashed line. It's not a part of the solution. If you want, you can make it a part of the solution. And one more thing. I chose this capital N there in the beginning as greater than 1. Okay, so I will keep that in mind. If n is less than or equal to 1, then integral of, say, f over 0, 2 can be written like this. Integral of 0, n f plus integral n, 2. Because of this inequality, we can split this interval into two intervals, partition them into two intervals, and use that property of integrals. All right. But now what? You see, we have already established this inequality for all n greater than 1, in particular for this value of n also. And that's why this thing is less than or equal to p divided by p minus 1. Now, if I do not write this and simply write this, can I claim that I will have this inequality? I will be correct, provided this is positive, at least non-negative. Is it non-negative? Yes. Why? That's because you recall one property of Riemann integrals, that if you are integrating a non-negative function, then the integral value is also non-negative. Are we integrating a non-negative function? Yes. We mentioned in the beginning itself that f, besides being decreasing, is also non-negative. And that is why this integral, whatever its value will be, is non-negative. So if I am not writing this, I am likely writing less. That's why this. But then this same inequality which was proved for n greater than 1 now is also true for n less than or equal to 1. That's it. That's how automatically those values also have been included. So this was our case that the series converges absolutely if p is greater than 1. Now we have to thus consider only that case where p is positive but less than or equal to 1, and here also the equal to 1 case we are going to handle separately. In fact, let's just do that first. But at the same time, let me also mention the results that we have used here. The one we have used prematurely and something else also. Actually, I should have mentioned it there itself. We have used the second fundamental theorem of calculus, and that is theorem 1194. And one exercise also. Exercise 10.4.3 part B. This is that exercise which tells us that no matter what this real number alpha is, if you differentiate this function, let me just use the standard notation, then this is equal to alpha times x to the power alpha minus 1. This is that result. We have already solved this exercise. So we can use this. And why do we need this? To ascertain that the antiderivative is that thing. Because it has to be differentiated to see that we get x to the power minus b, right? That is why. And also let's mention the corollary. Corollary means this corollary that we are proving is not used in the proof of the second fundamental theorem, that is theorem 11.4.9. So there is no danger of circularity. Okay, so now we are going to next consider the case where p is equal to 1. Next, let p be equal to 1. In this case, we have to prove that the series diverges. And for this, we have to bring in the logarithmic function. We know this, actually these facts we already know from our calculus courses, but we are yet to prove. These things will also be proved at some stage in this book itself. We know that the function ln. Ln means natural logarithm from the set of positive real numbers into the set of real numbers is monotonically increasing and onto. For this we have to wait for quite some time when we get to logarithmic function in this book and prove its properties rigorously. And onto. So for any, okay, so now again we will have to calculate another such integral, but this time we have to show that the series diverges. So we do not want the supremum this time to be a real number, it won't be a real number. We have to show that it also diverges, I mean the supremum is plus infinity. So for that we are going to choose any positive real number k. So for any k greater than 0, there exists an m greater than 1 such that the natural logarithm value of m is greater than k minus 1. Well, actually this m, no, I think this will not be enough. Whatever I wrote here may not be enough. Let me take this instead. I also make this greater than 1. Okay, now how are we getting this? See, again because now we have to simply rely on our prior knowledge of this function. So again, let's just see it's always best whenever you study analysis, no? If you can draw some diagram, please do it. That makes everything so clear. Unlike exponential function, the logarithmic function does take negative values. Say this is 1. The graph of the logarithmic function is roughly like this. It becomes 0 at 1, log 1 is 0. Natural logarithm means base e. On this side of 1 it becomes negative. On that side of 1 it becomes positive, but still it keeps on increasing. The rate of increase itself goes down, but still it doesn't really, it continues to go up, but the rate slowly goes down. It keeps on going down, but in doing so, in going like this, the graph of the natural logarithm actually covers all real numbers. That is why this function not only is increasing, but onto as well. Okay, so how do these two properties help us in choosing this m? Well, say your k is greater than 0, the graph doesn't look like it will really go up, but still we have this now. So that is why, because the graph at some stage exceeds k in value. So k minus 1 will be somewhat below that. So you can always choose some m greater than 1 at which the value, this is ln of m, will be greater than k minus 1, and at the same time it will also be greater than 1. But why do we need this? Well, we are going to need this here. So, again we are going to use some results that we will see only much later in this book. Theorem (1556). It's actually in the second volume, A and C, parts A and C. This theorem tells us properties of the logarithmic function. We have, so the thing we are now going to consider is the integral of f over the interval 0, m. First of all, so far we do not see any logarithm here, f is our f. First of all, because m is greater than 1, we can again, like before, split this integral into two integrals. This one, as before, is just 1. Alright. But now what is our f? What was our f in this type of intervals? Originally it was x to the power minus p. But now, because p is 1, this is x to the power minus 1, or 1 divided by x. Now, it is from this theorem that you know that when you differentiate the logarithmic function at any positive real number x, it is 1 divided by x. Do you recall this thing from school? And that is why the integrand 1 over x now has the antiderivative logarithm function. So if you again use your fundamental theorem of calculus, the second one, so it's just going to be ln of x evaluated at these limits. So this will be 1 plus ln of m. If you want, you can use brackets. I am not going to use it. Okay. Minus ln of 1, which is 0. Now ln of m is greater than k minus 1, or 1 plus ln of m is greater than k. K was our choice here. For any k, this thing is greater than k. In other words, in the set of all such integrals, no matter what k you choose, there always is an element which exceeds even that. So obviously you can keep on choosing larger and larger k. There is no bound to these integrals. You can find integrals having higher and higher values than even k, and that is why the set of such integrals here is unbounded above, and that is why their supremum is plus infinity. So, or hence, the supremum of these integrals, I am not writing m here because that m was that special m. N is kind of general. This is equal to plus infinity. Thus, by proposition 1164, no? These numbers, where is it? I lost, yeah, 1164. This time our series is divergent. If you were keenly observing, you may have noticed something else also. This proposition doesn't exactly tell us anything about this series, but rather a slightly different series where n starts from 0. However, for my convenience, I have decided that n starts from 1. Can I do that? Yes, I can, because by not considering n equal to 0, I am simply just not considering one term in the series. And one term or a finite number of terms, you already know from theory of infinite series, they do not matter. Well, they actually change the sum if the series is convergent, but the convergence or divergence, these things are not affected. If this series is convergent, then including 0 also, that series will also be convergent. While if this series is divergent, then inclusion of 0 will give you again a divergent series. And that's what we are concerned about here. We are not trying to calculate the value of this sum, infinite sum. We just want to say that whether it's convergent or divergent. Okay, so this was the case p equal to 1. Now we have to still consider the case where p is greater than 0 but less than 1. That's the final case. Next, let here also the it's somewhat similar to p greater than 1 case. The only difference is that now we will have divergence. The beginning may puzzle us, but that's how things are with analysis. We don't exactly see why we are choosing something, but only after doing the calculation it becomes clear. So this is what we now do. Choose an integer L which is greater than the maximum. So we want L to be a positive integer, and this may look quite involved, plus k times 1 minus p to the power 1 divided by 1 minus p. We will see why we need such a complicated thing. But before we do anything else though, let us see if this even makes sense. So the only thing we have to see here is if the base is positive. P is of course positive. K, oh, what is K? K was our that K, any K greater than 0. So K already is a positive real number, and because of this inequality 1 minus P is also positive. And that is why the exponent doesn't matter. We have a positive base, the exponent can be anything. But again, we have a ratio here. Note that 1 minus P is not equal to 0. So that problem is also not there, division by 0. So yes, this will be a positive real number, whatever it is. 1 of course is 1. So we are choosing L in such a way that L is a positive integer because of this and is greater than this real number. Okay. Now what? Now this is what we are going to calculate. The integral of f this time over the interval 0, L. We already know what to do. We first split the interval into two subintervals like this. All right. The beginning is complicated, but these calculations are really not. This one as before is 1 plus this one also, you know what it's going to be. So the original function is x to the power minus p. So the antiderivative is this. And when you put the limits, you are going to get L to the power 1 minus p minus 1 divided by 1 minus p. Okay. Let's keep it like that. Or should we, in fact, okay. Let's just write one more step. If you do whatever you do in such a case, 1 minus p plus this. So that will give you L to the power 1 minus p divided by 1 minus p. Now we go back to that thing. Now our choice of L will be justified. Because of how we have chosen L, L is greater than both of them. In particular, it's greater than this complicated number. Note that L is greater than this will imply what? Using the rules of exponents that we already proved way back, 1 minus p is greater than this. Note also carefully that because of our condition that p is less than 1, 1 minus p actually is a positive real number. And now it's very easy. Now you can perhaps see where we are going with this. Again, because 1 minus p is a positive real number, if I now divide both sides by 1 minus p, the inequality will not change direction. So this is equal to this, and this is greater than k. Hence, again a similar conclusion that the supremum is equal to plus infinity. So, by our proposition, the series is divergent. Eleven, 6, 4. This is divergent, and that completes the proof of the corollary. So that result from the 7th chapter that we have already proved for rational P has been extended in the same form for any real P. And in fact, if one considers this for complex numbers P and treats P as a variable, say one considers this. Let me write, instead of P, let me write S, where n is equal to 1 to infinity, and we treat this as a function of S, where S is now a complex variable, then you get your Riemann zeta function. And the Riemann hypothesis is about this function, the zeros of this function. It states, I am not very much familiar with the hypothesis, but it states that, if I am stating it correctly, that the non-real zeros of this zeta function, that is those complex numbers which are not real, but which if you put in place of S, you will get zero value. Those numbers lie on the line in the complex plane whose real part is 1 divided by 2. This no one has been able to prove so far. It's arguably the most important unsolved problem in mathematics right now. Teritau himself is after this, as many others are, but so far a proof remains elusive. Although there have been some minor improvements in the situation. But anyway, let me just end here itself. Tomorrow also we have an upload, because we have already done number theory last week. So tomorrow let's go back to trigonometry from class 11. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.